Hello students, welcome to this class of operation on sets. We are having union of sets. Given two sets A and B, their union is defined as A union B, whereby A union B, if at all, is being represented by X, then it means that is X belongs to A or X belongs to B. So example, let's talk of A having elements A, B, C, D. I remember we talked about elements in our previous class, and also B having 1, 2, 3, 4. So the union, which means you are going to combine the elements in A, B, C, D, and that is in A, that is elements A, B, C, D, combining them with 1, 2, 3, 4 to get now the union. So the union is just the combination of the elements in the various sets you've been updated to. Then we are having intersection of sets. The intersection of sets A and B is defined as this way. Here it is. We are having A intersection B. Of course, it is represented or denoted this way. Then we are having X. So if at all X is representing the intersection, then it means X belongs to A and X belongs to B. So let's check at an example for better understanding. We've got A is equals to A, B, 2, 5, 6. B, we've got 1, 2, 3, 4, 5, 6. So what we are trying to check when intersection, we are trying to check on the common elements in the sets we've been provided with. So at this particular point, when you try to check on set A, we are having 2, 5, 6. Here we are having 2, 5, 6. So 2, 5, 6 is common. So we are going to pick on that. And the difference between intersection and union is that we are having here with the intersection, we are having the conjunction and with the union we are having the conjunction or. So those are some of the things you need to check and master when it comes to union of sets and intersection of sets. When you talk of set complement, given a set A, that is we are having here given a set A, the complement of A is defined as, now we are having A superscript C, whereby we are being if at all is being represented by X, then it means we are going to have X belonging to the universal set and X does not belong to the set A. So if at all we are now having I remember talking about the universal set, and here at this particular point, let's say our universal set is having 1 to 9 elements, then it means if A is having 1, 5, 7, 8, we are only interested to checking now on what is featuring in the union set but is not featuring in the, that is what is featuring here and is not featuring here. So we try to check now if we're told 1 is in A, we are not picking to it, we are picking on 2 because it is in the union, we are picking on 3 because it is in the union, and 4 also, but 5 we are not picking because it is featuring in A. Then 6 the same, we are picking. 7 and 8 we are not picking because they are in the A set. Then from 9 we are also picking because it is in the union set alone. So with these ones we picked here, they are now the ones we refer to as the A complement because they are not in the set A. So set difference again, this is another kind of set operation whereby given two sets A and B is defined as A minus B, or you can say that is the difference of A with respect to B. So if at all is being represented by X, then it means X is in A and X is not in B. So therefore it means, so let's check on an example. Let's say our set A has got this, B has got this. So it means if at all we want to get now the set difference, it means we are going to check what is in A and is not in B. So of course when you check in A we have 1 here, so we are not picking on it. 2 is not in B, we shall pick on it. 3 is in the B here, we shall not pick on it. 4 is only in A, we shall pick on it. 8 is in B also, we are not going to pick it. And 9 is on A alone, so we are going to pick it. So we've only picked those that are in A but not in B. That's what we refer to as set difference. And what of it if at all it was the vice versa? So if at all it was the vice versa, it means we could have picked only on 5 because now 5 is the only one in B and not in A, of course, as per the definition we are having here. And I would also want you people to note that we are having this also means the same thing, the same difference of A with respect to B. Of course there's no A here, I was supposed to place it, I'm sorry for that. Then we are going also to check on systematic difference. When you talk of the systematic difference, The systematic difference of now, let's talk, we are having two elements, two sets, I mean A and B, that is normally represented with A small triangle B. So if at all you're having A small triangle B, then it means X, that is X belongs to A or X belongs to B, but not in both. Underline the word but not in both. So if at all it is not in both, then it means if at all, a good example, you're having A that is having this kind of sets and B having this number of sets, then it means the set difference, we're going now to check on what is only in, that is, yeah, it is in the both sets but is not featuring, that is, it is here, okay, I mean, and also it is here, but it is not in both of them. So if at all, for example, let's check, we are having A in A, so it is in A, it is in set A alone, we are going to pick on it. B, it is only in set A alone, not in B, we are going to pick on it. Then we check on C, C is featuring in A and B, we shall not pick on that. Then D, we are having D is featuring still in A and D, and B, I mean, we shall not pick on that. Then we are having E, E is featuring only in A, so we shall pick on it. F, featuring on A, we shall pick on it. G, featuring on A, we shall pick on it. But and also we can also talk of S. S is featuring in B alone, so we shall pick on it. T the same, R the same, and that's why I've also indicated that A intersection B complement still means the same. You can still use the same thing and get the same answer. If at all you've not understood, you've got the right to stop and also try to do some examples and some exercise on that. Then we have the Cartesian product. When you talk of the Cartesian product, the Cartesian product of two sets A and B is denoted as here. Cartesian product of two sets A and B is denoted as A times B, that is A, if at all you are having A, B representing them, then it means A belongs to A and B belongs to B. So a good example of it here, that if at all A has got this number of elements, B has got this number of elements, then it means A times B. We shall pick that A7, B8, that is, as you can see here, and we can also pick 6K, that is, as you can see. So with such kind, so that's what we are saying, that in such kind of a representation, we are talking of now Cartesian product or Cartesian kind of operation. Then we move on to index set, which is the kind of the last operation we are having. And when we talk of index sets, they are sets that when we are dealing with the multiple sets, say A1, A2, this is now when you're having more sets in one, you are dealing with them, we combine them using a simplified formula called a collection of sets indexed by alpha, so denoted as A, that is A lambda is equivalent to lambda belonging to alpha. So example, for each natural number n belongs to natural number, then we are having also the integers. So when you talk of k squared, we are having this an, that is in bracket we are having k such that k belongs to an integer, and also k squared is less than or equal to the n we are talking about here. So for n, this is just an evaluation we would like us to make, for example, but only for each natural number that is belongs to this. So we are checking on for n is equals to 1. So let's say a1 into bracket we have a negative 1, 0, 1. So if at all for n is equals to 1 with this kind of operation here, so you can check if it means that is k squared is less than or equal to 1 if at all n is equals to 1. So it means now that k squared is 0 or 1 itself. So it means k, if at all you try now to fix now this one, because we are talking k is an integer, and integers got negative and positives. Then we are talking of now it is less than n. So k, it means k to be negative 1, 1, 0.